Similar to what we saw with prisms and pyramids, the contents of 3 cones fill a cylinder with the same dimensions. A key concept, the volume of a cone. The volume of a cone is 1/3 the product of base area capital B and height h. You can use the formula to find the volume or missing dimensions. Example problem 2, using the volume formula. Find the volume of the cone at the left to the nearest cubic meter. Well, we know the formula. We also know that capital B represents the area of the base and that the base of a cone is a circle. Our circular base has a radius of 4 meters. We know that to find the area of a circle, we use the formula pi times the radius of the circle squared. In our example, the radius is 4, so we'll have 4 meters squared times pi. Or simply 4 times 4, 16, and in standard form we'll have the 16 to the left of pi, so the area of our base is 16 pi. Now note, this capital A to stand for area can really be thought of as capital B in our formula. And that may seem a little bit confusing. We're just using A for area, but our formula talks about B for the area of the base. So it's important to keep those things straight. So 16 pi becomes our base, so now as we rewrite our formula, it will be that the volume of our cone equals 1/3 of our base area, which we now know to be 16 pi, and more specifically 16 pi square meters, times lowercase h, our height, which noted from the image is 10 meters. So taking stock of what we have going on here, we'll have, well, first I'll consider the units. We have some meters squared times meters, so our final answer will be in cubic meters, which of course cubic would be the type of units to represent volume anyway. Volume equals, now we just need to identify what is 1/3 times 16 pi times 10, and I'll use a calculator. And here's my calculator. So I'll put my 1/3 in parentheses to make sure we avoid any PEMDAS, any unexpected or unintended consequences from PEMDAS. 1/3 times 16 pi, to get the pi button second, there we go, times 16 pi times 10. Alright, a quick double check. 1/3 times 16 pi times 10 looks good. And we get approximately 167.55, so about 168. I believe our problem asked us to find the volume of the cone at the left to the nearest cubic meter, so that's the nearest whole cubic meter, the ones place, so that will be 168 cubic meters, approximately. So our volume, 168 cubic meters, and I recognize that's not our exact answer. Since we're rounding, we really should not use an equal sign. Instead, we should use this approximately equal to sign. And a quick check problem, or 2 of them to be more specific. Number 2, find the volume of the cone at the right. Round to the nearest cubic meter. And number 3, find the radius of a cone with a volume of 360 cubic centimeters and a height of 9 centimeters. And I'll actually get you started on this one. I'll do some of the work, place some values into our formula, and you'll note that we have one missing value. We'll have one unknown, and that will be the radius of the base. So we'll begin by writing our formula for the volume of a cone. 1/3 base area times height. And now we'll substitute in what we know. We know that the volume is 360 cubic centimeters, so we can actually replace capital V. Note we're kind of working backward here. 360 cubic centimeters equals 1/3 of our base area times the height of 9 centimeters times 9 centimeters. Looks like we really want to isolate B at this point. Right? Our goal is to find the radius of the cone, and we know that, I'll take the time right now to write it over here. We know that our base area will equal pi times the radius squared. And our goal is really to figure out what r has to equal for this to be true. If we know, well, let's pretend for a moment that b was 20. Well, then we can solve for r just using some inverse operations. So let's figure out what b equals by isolating it in this equation. Change colors back to blue. Perhaps even first, 9 times 1/3 is simply 3, so we'll be dividing both sides of our equation by 3 centimeters. And note, dividing by 3 will actually take care of both of this 9 centimeters here, more specifically dividing by 3 centimeters, and this 1/3. Because, even though I didn't write it, we could have rewritten the numerator here as being just 3 centimeters times b. I kind of skipped a step there. Let's see how those cancel and we're just left with b. The same thing works. I just didn't show all of those steps here to the left. So we'll have b isolated, but we just divided one side of the equation by 3 centimeters. So we'll need to divide the other side of the equation by 3 centimeters as well. Went a little bit too far in my uncanceling. 3 centimeters. Dividing centimeters cubed by centimeters, well, that centimeters cubed becomes centimeters squared. 360 divided by 3, that's 120. So 120 square centimeters is the area of our base. Again, we're kind of working backward. We knew the volume, and we're trying to find one of the components, one of the other measurements of the cone. So that equals pi times our radius squared. Next, well, we need to isolate the radius, so we'd like to isolate the radius squared first. So we'll divide both sides of the equation by pi. I'll let you take over here, or I won't simplify it myself yet. I'll allow you to do that work as part of the quick check. But note, we end up with r squared, or our radius squared. As you know, the inverse of squaring is to apply the square root. So we'll end up taking the square root of both sides of this equation. So you'll need to find what 120 divided by pi equals, and then find its square root. Notice also, the square root of centimeters squared will just be centimeters, leading us all the way back to a linear measurement, just measuring a straight line like we would do with any distance, or with, in this case, the radius. So one more time, to finish out this quick check problem, 120 divided by pi, and then find the square root of that. That will give you a radius. And if necessary, round to the nearest whole centimeter. And check your understanding for this section, problems 1 through 4.